Good morning, everyone. It's my pleasure to introduce today's speaker, Jin-De Defense. We know Jin-De Defense for a very long time. He started at this department about 10 years ago. Jin-De, at that time, is very shy to me. He didn't talk much. And he said he wanted to do the modeling. And I challenged him. I said, are you serious about numerical modeling, or you just want to run a model? He, at that time, told me that he's serious about numerical modeling, but I didn't trust him. I said, no, you need to do something to prove yourself. So I gave him the most important model in my life, the VVM, and asked him, can you change the microphysics in the model? And he said, sure. That's Jin-De's style. He always promises everything, very fast. And then I didn't know it will really happen. At that time I think, oh, this is a challenging job. Changing a process in the model is very complicated, and it will take a very long time. But Jin-De really did it efficiently. So I further asked him, maybe you can use this model as a long-term goal in your life. He sort of hesitated a little bit, and then he decided to take the PhD course into today. So during that past 5 or 6 years, he spent all his time developing the VVM for the group, and used the VVM to test every hypothesis we have in terms of development. And then he tried to figure out what he wanted to do, and sort of focus on the topic of most advanced convection study under convection aggregation. So today he will talk about hierarchical understanding of the physical processes, modulating convection aggregation using VVM, of course. And then he will tell us, I hope, what he wanted to do in the future. That's where coming.
Okay. Thanks for introducing me by Professor Wu. And today I'll introduce the journey with VVM. Okay. So start with the convective aggregation. Why we focus on the convective aggregation? Because with the progress of the satellite observation, we can see a lot of cloud cluster. Okay, and over the tropical ocean, and these convection could be have a very different structure. Like here is an organized such as planetary wave, or like the here's sporadic convection, and also the large size organized convection. And previous study referred it to as a convective organization across several scale. And on the other hand, in 1993, Hell et al. Found that in an idealized call-resolving radiated convective equilibrium simulation, the convection will aggregate from the horizontal sporadic distribution to an aggregated state, and they call this phenomena as the convective self-aggregation, because they prescribe horizontal uniform SST, and without the bottom boundary forcing, the convection can spontaneously aggregate into a single or several patch. So they call this phenomena as a self-aggregation. And in 2018 and 2020, Edison Wing organized a model intercomparison project called RCMIP, and there's several models participated in this this project, and the model shows different states of the aggregate convective self-aggregation. Like scale is not so aggregate as SAM. SAM has a three aggregated Morse convection patches, and scale is like a sporadic convection. And these different states of the convective self-aggregation could be tested under different SST scenario, and using this different SST simulation, we can know how would the this convective aggregation will change under the warming scenario or cooling scenario. So we know so they calculate the change of the aggregation matrix due to the SST change. They found there are very diverse results across the models, and you can see half of model show the green, the orange dot is the substance fraction, the change of the substance fraction to the SST, and you can see half of model is decreased, and the other half is increased. So the result is the models cannot reach a consensus on the how a change of the convective self-aggregation to the SST. This result is also not surprised, because we know previous studies suggest that dynamical factors or physical processes can lead to a different status of the convective aggregation. So, for example, the Yannis et al. In 2020 showed that the development of convective aggregation is sensitive to the horizontal scale, like the domain size and the horizontal resolution, and when the resolution increases, the model can resolve some copol process in the boundary layer, and this copol propagation can lead to will destroy the development of the convective self-aggregation, while the physical process is investigated by Tompkins and Samir in 2017. They use different turbulent mixing parameterization in the models to test the effect of the the turbulent mixings to the impact of turbulent mixings to on the convective self-aggregation. And when the entrainment rate higher, the dry anomaly will develop from the upper level to kill the convection developed in the dry area, and this will enhance the development of the convective self-aggregation. When the entrainment rate is lower, the dry anomaly cannot effectively develop from the upper level to the lower level. So the convection can continuously develop in the dry area, and it will lead to the sporadic convection. And to understand how to understand this physical process in modulating convective self-aggregation in RCE simulation. So we we use the hierarchical modeling framework to proposed by Maha et al. In 2018. They proposed this modeling framework to improve our understanding of the physical phenomena or atmospheric phenomena using different degree of complexity. The model with different degree of complexity. So first, for example, like the dynamics hierarchy. To understanding the Rossby wave, they propose using the barotropic equation model to understand the Rossby wave propagation, and then use the quasi-geostrophic equation model to understanding the performance of behavior of Rossby wave propagation in a quasi-geostrophic equation model, and then step by step, we're adding the complexity into the model to understand the Rossby wave behavior in the complex model, and then toward the GCM and then real world Rossby wave propagation. So, to understand the physical processes influence the convective self-aggregation in RCE simulation, we first remove because it is the radiation and the convection interaction, and then lead to a quasi-equilibrium state. So we want to know how the convection will change due to the different physical processes. So we first prescribe the radiative forcing in the model. So we give the radiative forcing is the radiative forcing will unstabilize the environment and trigger the convection. So here we call it strongly forced simulation, and in this simulation the convection will develop, and we change the microphysics, as Professor Wu asked me to did it in several years ago. Yeah. So we have a old school microphysics scheme called Lin scheme, and then in 2015, Morrison and Melbourne proposed a new method a new treatment of the microphysical processes based on the particle properties by predicting the particle property. So this method can avoid the use of a predefined category of the cloud ice. So it can improve the efficiency of the microphysics, and also eliminate the redundant parameters in the core microphysics. So here we can see that because in VN Lin, the old school microphysics scheme, we can see because it divided ice particle into three categories. The first is ice cloud, and then snow, the green snow, and then purple is grapple. And you can see in the VN Lin, the convective system is always in the convective regions and stratiform regions. Here is always is occupied by a large mixing ratio of the grapple, and the terminal velocity of the grapple is smaller. So you can see the terminal velocity is smaller, and this grapple will melt around the freezing below the freezing level, and this effect, the melting effect will kill the convective object. So the convective objects in traditional microphysics, in the simulation with the traditional microphysics, will be weak. And on the other, compared to the traditional microphysics, P3 can predict the different property of the particles. So you can see in the stratiform regions, the ice sediment is slowly, and in the convective region, the ice is falling. Ice particle falls faster. So this fast falling ice can reduce the melting effect in the convective object regions. So in the P3, in the simulation with P3 microphysics, the convective system is stronger than the Vivian Lee, and you can see the precipitation spectrum under the convective cloud. You can see the red bars is the P3 microphysics is stronger than the Vivian Lee, and the extreme precipitation also stronger than the Vivian Lee. And with this strongly forced simulation, we know P3 tend to generate stronger convection, and the next step is, so could we use this understanding to further understanding the different microphysical processes would influence the convective self-aggregation. So we move to the convective aggregation simulation. It differs from the convective self-aggregation simulations. Let me explain why we remove the self-aggregation, the prefix of self, and because we first impose a SST gradient in the model, so the SST gradient will trigger the convection developed in the warm SST area, and then the convection will drive a substance, and also the inflow from the transport the MSE to the warm SST region, and the substance will have a drying effect to kill the convection in the cold SST regions, and the upgradient transport of MSE will enhance the convection developed in the warm SST region. This feedback will trigger the convection developed again. So this is a positive feedback called moisture convection feedback, and this will this feedback will enhance the development of the convective aggregation, and on the other hand, this is another feedback when we use the slab ocean, because the SST can respond to the surface flux and radiation. So when the convection develops, in the boundary layer, the wind will become stronger, and also the clouds will block the shock wave radiation. So in the region with the convection, the SST will become a cold anomalies, and then and in the region without the convection, the shock wave radiation will hit the SST, and then it will become warm anomaly, and the SST gradient will be reversed by the radiation or surface flux. So the inverse SST gradient will trigger another shallow circulation, trigger low-level circulation, and this low-level circulation will transport MSE from the convective region to the convection-free region. So it will trigger the convection in the convective-free region, and then you destroy the development of convection, convective aggregation, and we can use the initial SST gradient to control this two feedback and to control the moisture convection feedback, because when we give a greater SST gradient, you will trigger a stronger circulation. And on the other hand, we can modulate the convection SST feedback by modify the mixed layer depths. And because when we increase the mixed layer depths, the ocean will take longer time to respond to the short wave radiation, so it will decrease the feedback strength, the feedback strength of convective SST feedback. So we can use these two parameters to run a lot simulation, and then we use two different microphysics scheme to show how the microphysical process influence the convective aggregation. And in the upper right, in this phase diagram, the upper right region is the conditions favor the development of the convective aggregation, and in the lower left regions is the condition is not the condition is prefer the development of the sporadic convection. So we can see that when the condition is not favor the convective aggregation, P3 can still develop the circle. The circle is the aggregation develops, and the cross is not developed. So we can see the dashed line is the critical transition of the development of the convective aggregation, and we can see this line is compare the P3 microphysics scheme can produce the convective aggregation when the parameter is not suitable for development in Vivian Lee. So we can so we know that we use P3 microphysics scheme, the convective aggregation is easily to develop. So why this phenomenon will happen? So based on the previous study of the convective systems in the strongly forced simulation, we know that the convective system is stronger in the P3 microphysics, the simulation with P3, and we diagnose the convective cloud, the size spectrum of the convective cloud, because we believe that the convective system stronger, then it can develop larger. So we can see the P3 microphysics scheme have a larger frequency of the large size clouds compared to Vivian Lee. So from this study, we know when the large size convective clouds develops, it can enhance the development of the convective aggregation. So based on this understanding, we move forward to the RCE simulation. So we use the two model, is scale model from Japan, and the Vivian Lee professor who gave me. So yeah, so we carry out the simulation with 5 ensembles, and here I I only present the first ensemble, but 5 ensemble is consistent. And first we can see the in the equilibrium state. In the equilibrium state, we can see in VVN and scale the convective self-aggregation develops, and in scale the moist here is the precipitable water, and in scale the precipitable water is a little bit lower in scale model, in the moist region in scale model, and in VVN the precipitable water is higher in the moist region, and also the dry region also drier in scale compared to VVN. And so we focus on the development stage of the convective self-aggregation. We can see the blue line in the bottom panels. So the blue line is the substance fraction. It defines the development of the dry area. So it's an index of the convective self-aggregation to measure the convective self-aggregation. And you can see in scale the development of the substance fraction is from day 10 and sharp increase to 0.5, and then 0.4, and then gradually increase to 0.8 in day 50. And in VVN, the development of the dry area is sharply, the dry fraction is sharply increased from on day 15, and then to 0.8 in the day 30, and this development is sharp compared to scale model. So based on the understanding in the convective aggregation simulation, we further examine the size of convective systems. So here is the convective cloud spectrum. Is from in the scale and VVN, and we can see in the scale the cloud, the size spectrum of the clouds is mainly the convective cloud in scale is develops in the effective radius of the about 10 kilometers, and there's few larger size clouds in the scale when the convective self-aggregation develops. And in VVN, in the day 15 to 30, there's there's a higher frequency of the large size clouds, and also the occurrence of the large size cloud also consistent with the dry static energy export in the model. So the dry static energy can represent the strength of the circulation, convective self-aggregation circulation. So you can see in scale is the export of the DSE is gradually increased, and in VVN it sharply increased to equilibrium, and the equilibrium state is the export of DSE is greater than the scale, and this finding this understanding can okay, so we know that in the previous 3 study, we know that the convective cloud spectrum can represent a proxy of the how do the physical process modulate the convective self-aggregation. So So we know when the large size cloud appear, this cloud can efficiently drive the circulation, the convective self-aggregation circulation in RC simulation. But in our study, we also compare the two models, and also the description of this argument is qualitatively. So we want to further quantify the relationship between the cloud size spectrum and the circulation, and it's how it modulate the convective aggregation circulation. So first, we use the simple mathematic framework to formulate these two feedback. The motion convection feedback, because it describes the dry area expand, and the convection will develop in a certain region. But so the description of this phenomena is similar to the logistic equation. So we use the logistic equation we formulate this feedback with the logistic equation, and the other feedback is convection SST feedback. Because the description is it can destroy the development of the dry substance area. So we use the damping term to describe this feedback, and we assume these two feedback is linear. First, we just use this assumption and combine these two equation, and we can obtain a nonlinear systems with three equilibrium point. And here we give the bound of this equation is from maybe 0.5 to 1, and then we can know and the 0.5 it means that dry substance area is half of domain, and it represents the convection does not aggregate, and it maintains a sporadic distribution. And when the one is a little bit, one is here, and here is a maximum the capacity of the greatest substance friction, and it might be a 0.8 or 0.9, and it represents the state of the aggregated state. So we think this equation can better describe the critical transition of the the competition of two feedback. And so we use we would run more model using CM1 and using the same configuration and follow the RC MIP. And we first, because we want to evaluate because the equation is when this two terms is combined, it's too complicated to say which is better. So we first use we use the fixed SST configuration, and it can drop this convective SST feedback. So we can just use this equation to fit the substance friction. So we run 3 simulation of the fixed SST simulation with the 0.5 K SST gradient, and you will locate the convective aggregation will locate in the center of the domain. And here we just use this equation to fit the development of the substance friction in the 3 model. and you can see the VVN and CM1 have a similar value of the growth rate alpha in and while scale have the smaller growth rate, and you can see the maximum substance fraction in three models are very different, and so we want to connect these two factors to convex cloud size distribution. So it's a brand new result. And the first we can see when the scale reach the equilibrium state after 50 days, and I also plot this to check. It's similar to the day from 40 to 50, and this free figure shows that in VVN the large size clouds appear very frequently, and it is accompanied with the large substance fraction. And in scale, there's not so frequent, but also will develop in the scale. And the final, in the equilibrium state, scale can have also 0.8 of the substance fraction. And in the CM1, there's no large size. There's very rare large size cloud in CM1, and the substance fraction is the smallest in compared to CM1 scale and VVN. And in the developing stage, for now I cannot. I would say there's no significant difference between CM1 and scale. And however, in VVN, the large size cloud seems to have can enhance the development of the substance fraction, but in scale and CM1, it's not. There are not clear relationship between these two models. So I think this might be associated with some boundary layer processes, because we now investigate the substance fraction in the 5 kilometers in the middle of the troposphere. So this equation does not consider the influence of the boundary layer processes. So I think there might be the difference might be in the boundary layer, like the copole propagation or other the wind-induced surface flux exchange feedback, like that. And could we use an because it is too complicated to investigate, so could we just reduce the degree of the model based on the hierarchical modeling, the idea of hierarchical modeling? So we reduce the degree of a model. So we used another model called inelastic convective entities. It's developed by Guo and Neeling in the last 2 years, and they propose use inelastic systems and use the average to predict the average property of the convective column. So you can predefine the convective column like a cylindrical shape, or like the oval sushi, like a sushi shape. Okay, sushi roll. This is oval. Okay, so the result. Oh, Okay, so in this box, we have a convective columns, but it perturbed the model, and then convection will develop in the inner column. So the first column, inner column, is S1. It represents here is a blue circle in the circle. So this is the property of the ACE model, and then the S2 is the orange one, and so on. And the ACE number 8 is the environment. So based on this configuration, we can take advantage of the predefining the size of convective column in ACE. So we can test the convective. We can use a larger domain and predefine several size of convective column in the center of the domain, and then we can use this model to know how the different spectrum of the convective clouds to influence the large aggregation circulation develops. And however, for now, because the ACE model used reversible diabatic processes and simple relaxation of the hydrometeor to represent the microphysics. So for in the last 2 months, I think you have to have a complicated microphysical process to represent the convective system development. So I implement a complicated microphysics scheme, P3, because I'm familiar with the P3 scheme. So I implemented it in the ACE model. And for now, you can see the preliminary results. You can see the ACE in the cylindrical convective column simulation. You can see the gray shading is the clouds, and the red line is the vertical velocity larger than 1 meter per second, and the blue shading and this tiles is the rain. And you can see is the convection can develop and with the more realistic microphysical processes with the cloud envelopes and the rain can drop instead of the removal instantaneously when based on the relaxation parameters. So we believe use this configuration and we can design a new this experiment to understand the convective the influence of the convective cloud size distribution to the large scale circulation. And final, based on this idealized RC simulation and also the ACE model, understanding the cloud size distribution, how we link to the real world. Real world is this one, it's Himawari. And the others are the global storm resolving model like Nikon, Icon, or others. Yeah. So based on this idealized simulation, we want to understanding the convective organization in the real world, and also this can help us to evaluate the model, the convective systems, and the large-scale circulation in the the global storm resolving model, and it will provide provide understanding of how why model cannot represent the large-scale circulation or the convective system compared to the observation. And here's is the last page I have. So I will stop here and I will take questions, and thank you for all for for listening.
Any questions?
Yeah.
Yeah, very nice presentation. But I'm wondering, have you conduct any verification with the observational data to see which your result is more close to reality? Because you see, as you show a strong sensitivity of your simulation result to the microphysics schemes. And so, which one can we really trust?
I would say no one. Yeah, yeah, because we just use the idealized configuration to test model sensitivity and to understand the convective aggregation. However, in the real world, there are several factors can influence, like the SST, like for example, SST gradient, and also the large scale circulation will influence the convective systems, and so I cannot to say which one is better, but for the in the idealized simulations, the precipitation spectrum, especially in P3, is can better capture the extreme precipitation compared to Linsky. So I would say P3 microphysics scheme in the convective system generated by the P3 microphysics scheme would be closer to observation. Yeah.
But you say trust no one.
Yeah. Because even though the result is similar, the process might not be correct. So I only say it's close to observation, but not observation. Yeah.
A quick question is, in the end, you're talking about the importance of convective organizations. And what you see on the center picture is a lot of convective organizations. But convective organization is not exactly the same as convective aggregations.
Yeah.
There are so many other important mechanisms being discussed and explored.
Yeah.
So that you have a process. So, a very quick question, technical questions. You finally mentioned about the alpha, but what about the beta? You show these two equations, but the end result is depending on what is alpha and what is beta. Otherwise, you can even the two simple equations you can have many different regimes to discuss. So you show us the alpha, but for some reason I didn't see any beta. What is the beta?
Yeah. No. 不是贝贝要地埋吗 ？Okay, so what's wrong? Okay, so because there are three models, and because when the model have to implement the slab ocean model to compare three models. So for now, I only have the slab ocean in VVN, and the other two models are still I'm reading the code and then try to implement the slab ocean model in CM1 and scale. So for now, I only can test the VVN, the beta of the VVN, and the other two models cannot perform the testing. But I would say the beta is the the coupling strength of the boundary layer and the SST. So it might be like how to, yeah. Also it also associated with the convective clouds. So for now, I'm not clearly think about how to interpret beta. So in this situation, I think I cannot clearly think about the beta, and technically I cannot perform the simulation in the other two models. So for now, I just investigate the alpha and the maximum substance fraction for now. And in the future, I will further test the beta in these three models. So, yeah.
Any more questions?
Thank you, Jin-De, for your talk. Following Professor Paul's last question, you are using these two equations that represent two different feedbacks to interpret your model results. But there are other important mechanisms for feedbacks in the RCE simulations. So how do you consider other feedbacks, such as one-way feedbacks and other radiative feedbacks into your formula to make, to verify or justify your alpha and beta?
Yeah. So for the there are several studies show that when the convective self-aggregation develops, the long-wave feedback is important for dry area develop. However, in our simulation configuration, because we force the development of convective self-aggregation, and the substance of the substance will balance with the long-wave radiated cooling in a dry area. So I think when we force the aggregation develops, the feedback of the other feedback will become minor, and this moisture convection feedback will become dominant when we use this configuration. And I think because when we move to the convective self-aggregation simulation, we have to consider other factors, the importance of the others. Yeah, that's my opinion. Yeah.
Let me ask you, the P3 microphysics scheme, overall during your simulation, would that lead to a greater ice latent heat release or less? Because it's not just, I know it's a particle size shaping, and that can cause the difference in the extension because of their falling speed. But the other thing I'm curious is what is the total latent heat release from the ice? Is that increase or is it pretty much the same?
Yeah, we also investigate the difference in the precipitation, the amount of precipitation, and in the P3 and Linsky, the precipitation, the domain average precipitation is similar. So the latent heat release in the atmosphere will be different. But another issue is that even though the amount is the same, but the shape of the heating profile could be different. So maybe in the P3 microphysics, because we also found that the P3 microphysics can have horizontal extended envelope clouds, and it might be great. It might have a greater heating, a strong heating in the upper level. So, but I don't have the figure to prove that. So it's the hypothesis. Maybe the heating profile, the difference in heating profile will lead to the difference in driving the circulation. Yeah.
I think we have that figure in the paper, so
Right.
maybe we can check later. I do remember we have the latent heat release profile in the isotropic space, so we can see how much it does change across two different microphysics.
Okay.
Okay, maybe later. Any more question? Yeah.
A very interesting result, and I'm curious about when you plot the size distribution of the convective cloud. There are two peaks, and one is about 10. Yeah, that one. And I'm curious that when you are talking about the future world with the ACE, you want to try to find out there's a criteria area that will make the convective cell to aggregate or not. Is your purpose to one of the purpose to do the AC in the future? I mean that because there's two different peak, right?
Yeah.
There's a larger and small convective cells.
Yeah.
And in my understanding, the convective cell want to aggregate their cell merger process. And I'm curious, because there's in the middle, there's a less distribution of the convective cell. Is that imply that in the middle of the size actually is more apt to going to the larger size and the smaller size? So in the equilibrium state, there's a critical point that will make the process into a different pathways. I don't know, in your AC, you are trying to do that because you can try to convert the cell area and the cell together, their distance, they will affect the aggregation rate or something. Yeah.
I think this is a very good question. Can you go to the next slide? Yeah. Yeah. So can you tell us about the x-axis? What does it mean in the S model?
Okay, so the x-axis is the different columns of the ACE model. So because in the ACE model you can just you have to predefine the size of the convective column. So so in the inner the column 1 is the inner column, and then the column 2 is from 5 kilometers. The area from 5 kilometers to 10 kilometers. So and so on. So in the you can also just use single only one column to represent the convective system. So you just imagine this cylindrical column is only one column, and then based on this configuration, you can I can just use different size of the column to embed it in the RCE, embed it in the larger domain, and then see the effect of the convective cloud. And you also mentioned that the aggregation process is the merging of the convective systems, but this process cannot be represented in the ACE model, because for now the model have to predefine the column and cannot change the column when the simulation is performed. So I would say I can prescribe the convective column based on the size distribution in different model and prescribe into the ACE model. But I cannot just apply several small convective column and then make them merge together when to mimic the development of the convective aggregation. And yeah, maybe I can because for now we don't have a better governing equation for the convective area, so for now it's impractical. So yeah, I only can investigate the difference in the convective cloud size spectrum to the influence of the spectrum to the large scale circulation. Yeah.
There's some strong words in your ACE. I know this is more something new, but anyway, you can't explain it. Seems to me that's a very serious business. Reversible diabetic process. How this is going? Seems to be a very serious business. Can you explain why this process is not fighting or contrast to whatever the numerical simulation, or they are the same? It's a reversible diabetic process.
Yeah. So the reversible adiabatic, or I spelled the wrong words.
You say that.
Oh, okay. Adiabatic? Oh, I'm confused. Okay, it's maybe 等下非绝乐 adiabatic 绝乐是 adiabatic 啊，这是的。
Use MSE.
Yeah. Yeah.
This is something different.
Yeah.
Very interesting, but this is not.
Yeah. I just explained it's a conserve of the moist moist steady energy, and then so without the simple relaxation of hydrometeors, the total water or the total water will be conserved. So it's very simple. Just when the condensates appear, that the model just remove locally with a tight scale. So I think it's
like pseudo-adiabatic.
Yeah.
So is this similar, what you're thinking is similar to undiluted ascent? Tropics,
Yeah.
Undiluted.
Yeah. So but when the multi-column ACE is simulated, the inner column can dilute it to the outer column. So but total in the all column of the model will conserve the moist steady energy. So I think it's not complicated to represent the process in the cloud resolving in the RC simulation. Yeah. So I want to change the configuration to I want to change the microphysical processes in the ACE. Yeah.
For your reference, Dr. Jian Muhua also applied only the reversible diabetic process in his model to calculate RC simulations. Maybe you can discuss with him on this topic later. Any question from the online community? ESC
真的吗？不好吧？
其实早就断线了。
我断线了吗？国风没有说啊。
Question from the online?
Yes, should we ask a question now, or is this the type of coming to ask a question, or there's no difference?
Depending on the atmosphere, I will encourage more discussion. So please go ahead.
My questions were similar to previous ones, but I guess I want to follow up. Professor Young asked about given these feature comparison, how do you know which model perform closer to observation?
Okay, good.
And with that, I have two follow-up. One is the answer to that question about a particular model or scheme is closer to observation, and I wonder, how do you know that? That's the first question. And the second is that I like how you perform all these understandings throughout a hierarchy, and great talk, by the way. And to proceed further, it looks like you wanted to use these understandings from self-aggregation or RC simulation to the simulations where it's probably working. And I wonder, based on your experience or intuition, how would the mechanism is linear self-aggregation and others that are forced by SSD gradient or large scale? Do you think, or in other words, how do you bring your insights into a real world situation where there are really strong large scale processing that force open models to perform more or less more similarly than these RCEs or comparison?
So the first question is how did I say which model is better? So for now I just use the precipitation spectrum to say P3 is better, but maybe on other metrics like maybe the envelope clause size or like the convective object strength, maybe lean scheme or the scale model can have a better performance, but I'm not sure. So for now, I just based on the precipitation spectrum to argue that P3 can have a better performance on extreme precipitation. So it's more closer to the observation. Yeah, that is the question for the answer for the question. The second one is
what is large scale? What is convection application?
What is the? Because just like Professor Guo say, the convective self-aggregation and the convective organization is different. And in the real world, the convective organization is came from the convective scale to the planetary scale. But in the idealized RC simulation, or in my study, in our study, we only just use a certain domain size to argue that the convective clause is convective scale, and driving the aggregation circulation to have a moist patch and dry regions is a scale larger than the convective scale, so we call it the large scale. But when we want to move on to when we want to apply this understanding to the real world, we have to make to have how to say that, the separation of the scale to argue that, but the MJO is we would say is a larger scale convective envelope propagate around in the tropics. So the convection is I would say it's hard to separate, but for now I just base on the result in the idealized simulation. So when we further apply it to observation or global storm resolving model, for now I don't have a clear idea to separate them. Yeah.
ChatGPT summary, it's all convection.
I just want to know your thoughts there. If the other question that I also want to know your thoughts about is that I was hoping you can talk more about the process in the boundary layer when you make the linkage between in the very last project, when you make the linkage between cloud size and subsidence, and you briefly mentioned how this could be due to boundary layer processes. Would you mind elaborate a bit more?
Okay. Wow. So because I just use the substance fraction in the 5 kilometers, so it is the proxy for the convective aggregation circulation, and the result will include the convection. The convection drive the substance, and also they might be influenced by like a copper propagate from the convective region to the non-convective regions. So I think it might contain some of them, but not. It could be more. It was to further investigate how because for now I see that the substance fraction grows with the different growth rate and different rates, but the convective system the spectrum of convective cloud size is not have a much many difference. So I will speculate that there might be some process in the boundary layer, such as copper or other process can influence the development of the substance fraction. That's my speculation. Yeah.
Got it. So you're saying that by performing these additional fixed SST simulations, you cut off the potential feedback in the whole pool, and you no longer see the difference in the growth phase. And that's why you think that it's the coupling between the two that leads to the differences. I'm just there.
Yes, sir. No.
Yes, I can.
We can talk to others, but thank you.
I can perform this. Like the simulation, remove the rain evaporation to suppress the copper formation. So I can justify the role of the copol in the experiment in this configuration. Yeah. Yes.
Yes, you can.
Yeah, I can. Okay.
Thank you.
Okay. I want to ask very similar questions like Yanting, but when we ask you about how to evaluate the models, your answer is actually related to convection organization. And then we ask you about the large scale, and then you mentioned MJO. So my question is, maybe you can evaluate the models using your logistic equation and help us understand the real world convection aggregation or the MJO using your logistic equation. Will that be easier? Because in terms of subsidence fractions and also the change in large scale SST and moisture, these are actually the easier observables for the real world. And maybe we don't need to get to the details of all the convective systems in the cloud resolving model yet, but we can start asking whether these these cloud resolving models are giving us the relationship between the convection and the large scale circulation in the ballpark of the real world. How do you think?
Yeah, we can. We can using this equation set for the to diagnose the growth rate or the substance fraction in the real world. But because in our simulation configuration is forced by the forcing in the boundary using SST gradient. So under this situation, I know that the substance fraction will develop and the convection will develop in the certain regions. But in the real world, there are several factors can influence the substance fraction or the growth rate. So I think I can do the diagnostic, but I will struggle in how to explain why the substance fraction or the growth rate increase or decrease.
Struggle is good. Please. What would you do? Can you propose some strategy? I know it's difficult. Otherwise,
yeah. So
I will not ask you this question.
Okay, so for I think maybe it could follow the Tsai and maps. The method they use first. We define a 5° plus 5° box, and then use the reanalysis data or the satellite observation to evaluate the maybe SST gradient or the relationship between the SST gradient and the substance fraction evolution. And we can have a lot of the bugs, and then we can obtain enough statistic to argue that maybe they have relationship on when the large scale more large scale circulation is not evidence, and the local SST gradient can control the development of the organized convection or the substance fraction, like that. So there's several studies using the observation data try to identify the convective organization in the real world. But not bird. I think maybe I can try.
So I think you're developing, or at least in your thesis, you're trying to establish a hierarchy to understand convective aggregation. Can you first plot a schematic diagram on Blackboard to show us the hierarchy of your 3 papers, or maybe the hierarchy you are talking about? And then my next question is, maybe we can actually understand the real-world convection aggregation using this hierarchy. Do you know my question? So here you are using the VVM as a tool, or to build this hierarchy, so that we understand all this convection aggregation in the world of idealized simulations. But maybe we can learn or use this hierarchy as the tool, and we can plug in or think about the strategies to analyze the real-world observation or the global cloud resolving models, and to evaluate their aggregation. So first, a schematic of your research, please.
Hey.可以用那个，但那个很糊，那个很糊。
更模糊，关掉，关闭，全部移除。好，可以，清楚了。
哎。Explain. Thank you.
It's a V shape.
Yeah, because when I develop model, I love the multi-grid with V shape. So the idea of multi-grid is, well, no, it's not multi-grid, it's hierarchy. Oh, okay, so we start from the, oh, okay, so. Complexity, okay, is more complicated, it's less. So from the beginning, we start with a strongly forced environment and then increase the complexity of the model configuration. We use the slab ocean to force the convective aggregation develop. And finally, we evaluate compared to the convective self-aggregation in between the 2 models. So we step by step increase the complexity in the last several years. And then, so now because we found that on this side, we just found the cloud size distribution and the convective aggregation circulation can be linked together. So, however, the cloud size spectrum, when we add in the scale model, it becomes in this simulation, we think is complicated. So we just use the fixed SST simulation and the logistic equation to quantify the effect of the. We want to quantify the effect of the cloud size spectrum to the large scale to the convective aggregation circulation, and we still found that it's also found that the growth rate and the substance fraction might be that they have some relationship with the cloud size spectrum, but I cannot. It's hard to argue that when the large. I can only argue that when the large size cloud appear, the substance fraction could be higher. And so in the developing stage of the convective aggregation, there's things to be independent to the cloud size spectrum. So I want to use a more idealized way to investigate the role of the cloud size spectrum using the ACE model. So it's like a V shape. And then if we have another process or feedback, we want to investigate, I think we could just hit from here to here, just like a V cycle.
Oh, so next you are going to work with the Nikon model, right? So the Nikon model will have a simulation. So how do we fit in Nikon?
Where is Nikon on this plot?
Why?
Yeah, because I think in the Nikon model, it's more complicated compared to RC simulation. It has rotation and also the terrain and other forcing like that. So I think it's more complicated to the RC simulation. So you will locate it in the most complicated side. And if we want to know the different microphysics, the impact of different microphysics in Nikon. So first, I think we have to have a target like Typhoon or MJO, and then we can simplify the for example MJO. I would say I will first reduce the complexity, like remove the terrain, just use aquaplanar simulation and aquaplanar simulation and fixed ST. Okay, so just like a Nikon, and so maybe from the aquaplanar aquaplanar simulation to with fixed ST, T 是这样写吗？T, and then first we can evaluate the cloud, the performance of the MJO in the aquaplaner simulation, and then maybe we can understand the surface flux feedback or long wave feedback is important, and the different microphysics will lead to the different circulation, and then maybe we could move further to also aquaplanets, and maybe with the slab ocean to investigate the air-sea interaction, and finally we could link the understanding in these two simulation to the real world phenomena, and if I'm good at math, we can just use a mathematic or other maybe like a two column model, simplified two column model to have a consistent result in maybe maybe like a Gill solution model with the prescribed convective heating, or maybe simplified convective skin to understand the I think it's from the it's the model and the variable, and here might be data. So like a V shape to understand the impact of different microphysics on MJO. Yeah. But the V will be like a very bottom of the.
For your reference, Dr. Soimas did a similar work on aquaplane and Nikon, studying MJO and convection aggregation. So, Hiro, do you want to ask some questions? Hello, are you there?
Yes, I'm here. Yeah, thank you very much for your interesting talk. And you are coming to Japan and doing some research of using Nikon. I understand. Anyway, I want to know your opinion about the current status of crowd resolving models. Do you have any idea to convert diverse behaviors of crowd resolving models to the nature? I'm wondering if our model is a model of the nature or not. And do you think about that?
Is Vivian true?
Your results of perspectives, our physical model will be beaten by AI models in here, the AI models here predict the behavior of moisture much better than our physical models. That is my current understanding of AI models. So we need to know how to manage moisture in models. And in my opinion, we are lacking something in our CRMs. So I want to know, how do you think about that? Because you are becoming a PhD from this screen, so you need to sound.
I would say model is not the observation, and the model can help us to understand some phenomena or physical processes, and help us to build a theoretical understanding of the phenomena we focus on. And so I don't want to say Vivian is true, and Nikon is also not the truth. It's not the real world. So, but they can help me to understand the cloud size distribution to the linkage between the cloud size distribution to the aggregation. So is my opinion to how I think about the model and observation. And yeah, but Chen-Ming would say Vivian is true. Oh, okay.
I said Vivian is right.
Okay. Okay. So,
Please be a better scientist.
You still have many years to work on.
Yeah. For how to know, because just like you say, there are some phenomena will not be truth in model, so maybe compared to the observation is needed, but could we? I think I was still based on the thinking of the hierarchical modeling from just reduce other factors and focus on the factors that the phenomena seen in models but not found in the real world, to validate, to create a theoretical understanding to judge this is the model bias or there's the mystery in observation we cannot, it's the mystery we cannot observe in the real world or not, or others. So before saying which one is true, I will prefer to say to use this framework to investigate these phenomena. Yeah.
Okay. Yeah, if I understand, we need some methods to reconstruct multi-scale nature of graphs, and ACE may be an interesting approach that you find that. That's all.
Oh, okay. Thank you.
Okay, so do you want to ask questions or?
Okay, so although I'm in your committee, I have to say I know very little about convection. So just the question I have is just what sets the horizontal scale for this convective cluster? Is it just in your square domain simulation? It seems like it forms one eventually at the center, but just from the inter-model comparison, I at least saw 3 clusters in. And so I guess just, but at the end in your this kind of more like a channel type of simulation, you again see only one. So what's the say if you increase your
Domain size.
Yeah, or you see what basically if you only see one, that tells you this horizontal scale is somehow limited by your domain size. But it seems like in the model comparison, there is certain length scale emerge, and so I just wonder what's for the state of knowledge, what sets the horizontal scale.
Yes. Yeah. What shape the scale? Okay. Yeah. I think because the maybe the propagation of the damping rate of damping rate of the gravity wave in the free atmosphere might be important factors, because when the convection develops, it is a discussion when we developing ACE model. We just with the Yihong Guo, and we just discussed how far the substance will develop. So when the convection develops, the first mode or the second mode will propagate outward to the environment, and the environment radiated cooling and the gravity wave, the speed of gravity wave propagation will reach an equilibrium, and then the substance will just the range of the substance will be contained in this damping rate and the propagation speed. So the substance scale might be determined by this factor, but I'm not sure that there's just why the model have the different scale, because we can consider the gravity wave source like a convective system. Maybe a larger system can have a different, maybe like different heating rate or the different shape of the heating profile. And then when it propagates, maybe the convective system can, one model is the 3K and the other model is 1K, and the propagation and damping will be 1K will be damping, will be damped faster, so it cannot influence more far away from the convective system. So, and the other factor is the water vapor in the free atmosphere. It will influence the radiated cooling, and the radiated cooling can influence the damping of the gravity wave. So I think the scale of the substance will also be influenced by the physical processes in the among models. So yeah.
My question is even simpler. I just say, for example, if you elongate your channel,
yeah,
do you see a length scale emerge from this cluster? For example, I mean, you guys all know that you study airplane stability. There is this certain scale emerge, and that's most stable scale, length scale. And for this case, is it useful to think that way or not? Is there an emerging length scale?
The elongated domain, we.
So yes or no?
It's okay if it's totally
I want
no.
to start it from yes or no, then you start explaining.
Because I have no idea, so I just want to.
But the question, maybe, let me put it the other way. In your study, you try to show the subsidence fraction. So that's a normalized with respect to your domain, right?
Right.
And that's important. If you have larger subsidence fraction, presumably your convection is stronger. But if the model produces the right scale and everything, CSA is this portion of the convection, it's always the same because that's accurate, predicted. Let's assume that. But then if you enlarge your domain, then your subsidence fraction will be different. And how do we understand? Maybe that's a way I put Sunan's question.
Yep.
Or or if this your CSA is proportional, your size is kind of different in a different domain.
Oh, okay. Yeah, I would say the substance fraction for this simulation and 4 types of the domain size will be similar. It's maybe because when we have performed the large size. It's not the elongated domain. It's a square domain. It's the results from compare VVN and scale. We found that when the domain increased to 4 times larger, it can also, in VVN, it only produce one cluster. And so I was saying that in VVN, the substance fraction will be a constant when the domain size change. Maybe it cannot reach the scale of the substance, the scale of substance. So
then would be if the substance fraction is kind of independent of the domain size you are using.
Yeah.
Would that imply your cloud cluster
become larger?
Yeah. Their size is domain dependent.
Yeah.
But in real chemistry, I would think maybe should the cloud cluster or something, or maybe there's a wide range of a cloud cluster, hundreds kilometers, 2,000 kilometers, or
yeah.
Right.
Yeah.
So maybe it's still unknown just if there's a preferred length scale that will emerge. Is that kind of community thinking?
If you ask me,
yeah.
Can I answer?
Yeah, sure.
I think a better question is what sets up the scale of the moisture, the water vapor. That will be critical in this kind of study.
I mean, when I see the setup, you impose, when you verify for the later experiment, you verify your initial SST gradient. I just want to, when I see that, because that gradient imposes a length scale also. So when I see this, because your negative feedback one, that is set by the convective cell size. SST gradient is whatever you can choose, the length scale you can choose. And there's another domain size. So there's at least 3 length scale that kind of involve. And so I just try to figure out what's the, because those those the size of this red and blue may be totally different. Because the left-hand side, you choose your SST gradient. You can impose whatever gradient length scale you want to have. But this on the right-hand side is set by the emerging length scale, if there is any, for the cluster, right? Because that's the unique cloud and that make the lower layer wind faster or make the latent heat flux greater. Anyway, I just want to.
Okay.
I always feel that I know we're talking about science, and we are interested in science, but often Morg is very good at also technical details. So it's something we may not worry that much, but during the period, I saw the concern about all this technical detail. Like never been mentioned about when you're talking about energy equilibrium, the type of business, the domain size, the vertical boundary condition, and all this kind of things is very crucial and critical. But I guess you didn't say very much. I know Morg knows all the take care of all this detail, but I would encourage you to look carefully. And I'm wondering also when Sunan talked about all this, I think the moisture and the radiation, the real radiation may be important. That may be related to your beta effect. The beta parameter. And that beta parameter will set up whatever your final fraction equilibrium will be. It's a ratio. I think it's a simple way out here. It's a 1 minus the ratio of beta divided by alpha would be your fraction ratio. But the beta really seems to me is quite challenging, and maybe radiation dependent.
Okay, I think we have discussed a lot.
We have tortured it.
Yeah. We are looking forward to the future, and wish or hope Jin-De can be that person to answer this question with us or for us.
I try my best.
Yeah, and
Record.
Yeah. Always recorded. So I think it's a good time to close this seminar. So we have some administrative stuff to work on. So please, the students can leave.